Okay. So hi everybody, and I hope you you are good in this tough period. I'm about to share my screen. So this is a joint presentation made of two parts, two sessions. The first given by me, and it is about IO control. The other one is given by Anders, and it's about kernel testing, still related to related with IO control. My part is longer. I'll try to keep it as short as possible. I'll skip some slides. If something is not clear, just stop me or ask me after we have finished it, as you like. Of course, happy if you stop me. So as for my subsession, also my subsession is made of two parts. In the first part, I'll tell you the state of affairs, so the state of the art, and I will talk about these two new IO controllers that are now available in Linux, and I will report on what happened. It happened that I have compared them with BFQ, and I have seen that results are extremely bad, because just trying some common workloads, I've seen that these new IO controllers just fail. They fail to control bandwidth, they fail to reach a high throughput. But what is missing in the picture is the reason why these controllers fail. So the main goal of this presentation is answering this question: why do these new controllers fail? I'll answer with an analysis, somehow an in-depth analysis on these controllers. So what is the use case of interest for these controllers? The use case is when you have multiple entities that are competing for some shared storage. Examples of entities are processes, groups, containers, virtual machine, any active entity that may compete for storage. And the goal is to guarantee to each of these entities a bounded latency and or at least a minimum bandwidth. Of course, we are talking about IO here, so IO latency, IO bandwidth. In this respect, the typical mainstream solutions are extremely inefficient, because they waste almost all the speed of the drives, up to 90% of the speed of these drives. You can find all details in this article published on Linaro blog. There is a solution to this problem. The BFQ IO scheduler does face this problem and actually reduces this waste of speed to actually practically nothing, no waste. But BFQ, for a series of reasons, is not yet a common solution. So in this situation, Facebook people have, Facebook developers have contributed with two new IO controllers, the IO latency controller and the IO cost controller. The first controller associates a target latency with every group, and then it throttles group so that the target latency of each group is met. So you assign a latency to every group, the latency that you desire to satisfy for that group, and the controller tries to satisfy that latency target. The IO controller, on the other hand, associates a weight with each group, and again, it throttles group because it works with the same identical mechanism. Both controllers work by throttling IO, but in this case, it throttles group so as to let each group get a fraction of the bandwidth, of the total bandwidth, a fraction proportional to the weight of the group. So the higher the weight, the higher the bandwidth. In addition, this bandwidth is inversely proportional to the cost of the IO of that group, cost in terms of time, how long it takes to do that IO. So the more costly the IO of a group is, the lower bandwidth that group gets. The idea is to avoid that groups doing very costly IO kill the total bandwidth of a drive. With this scheme, you can also provide latency guarantees indirectly by giving the right bandwidth to a certain group. You also guarantee it a certain latency. Now, how do these new proposals compare with BFQ? Well, BFQ does exactly the same thing as the I/O cost controller because it associates a weight with each group or even each process, but this is not that relevant. But then the mechanism is different because BFQ does not throttle I/O, but it schedules I/O. So it decides the order in which I/O is to be served. And it schedules I/O so has such that each group gets a fraction of the bandwidth proportional to its weight. It's the same as with the I/O cost, the I/O cost controller. To avoid that slow I/O, also in this case, kills throughput, slow I/O gets guarantees in the time domain. There is this detail, but I don't want to steal you time on low-level details about BFQ. And to finish about BFQ, as with I/O cost, you can have latency guarantees indirectly by setting bandwidth guarantees. So as I hope you have seen, the goals of these new controllers are the same as BFQ, latency and bandwidth. Yet no documentation is available on when one should use these controllers and when one should use BFQ. So this motivated me to compare these controllers with BFQ to find out when to use one, when the other, what is the performance of these controllers and compared with BFQ. I made this comparison. I have, for example, you can find my results in my presentation for Last Connect. I measured the ability to guarantee bandwidth to groups and latency to groups, and at the same time to reach a high throughput, high total throughput. What was the result? What is the results? BFQ outperformed these controllers. For example, on an SSD, with BFQ, I recorded up to 47 times more bandwidth than with I/O cost, and up to 3 times more total throughput. So really outperformed them. So why? Well, it happened because for some workloads, these new controllers simply failed to control I/O. They failed to provide the expected guarantees for latency and bandwidth. They failed to reach a high throughput. Okay, they failed. But why did they fail? So this is the goal of this presentation, telling you what I found out about the why. I will focus only on I/O cost because I/O cost is more complex and accurate than I/O latency. So my result with I/O cost apply also to I/O latency. I will show you only 3 of the workloads for which I/O cost fails on the drive that you can see on the slide. You can find a full description of the plots that I'm going to show you and full results once again in my previous presentation. So here's my first example. Let me tell you what is on this plot. So in this plot, I'm showing throughputs for workloads that are generated by 2 types of sources. The first source is a group that I call target, and this is our probe group, the one that we want to use to measure the bandwidth or the latency that can be guaranteed to a generic group for any workload. The other groups are the interferers. Their goal is just to generate I/O to interfere with the I/O of the target. Here you can see that what the interferers do. So there are several workloads. You can see that in the first subplot, so the first workload, interferers do just random reads. Second subplot, random writes. Again, random reads, random writes. And then there are the different possible workloads for the target: random read, sequential read, sequential read. So the various combination in this set of workloads. This is just one of the many plots that I made. So in this case, I'm comparing basically interferers that do random I/O against a target that may do either random or sequential I/O. Just reads. Okay, so what do these plots show? They show both the throughput, the average throughput during the test of the targets, it's the bar in pink, and the cumulative average throughput of all the interferers, that is the bar in cyan. Finally, as a reference, there is the total throughput that is reached if there is no control on I/O. Usually, in that case, the total throughput is higher because the drive is free to do any optimization, any possible optimization to get the maximum possible throughput. Of course, the sum of the heights of these bars gives the total throughput. Finally, what else? There are the schedulers under test, the two solutions under test. One solution is the cost, the I/O cost controller, and the I/O cost controller implements an I/O policy that is called cost. So in the first bars in each subplot report the results for the cost policy. You can see both policy and scheduler. In case of the cost controller, the cost policy, the scheduler is known because all the I/O control is in the hands of the controller. Then there is BFQ as scheduler, and the policy is the proportional share policy, which is exactly the policy implemented by BFQ. So what do we see in this plot here? We see that with cost as I/O controller, the target eats all the bandwidth and the interferers don't get anything. Consider that interferers, if I remember well, are at least 7 or even 14. So all these interference altogether get almost no bandwidth. So total failure in providing reasonable bandwidth guarantees. With BFQ, you see that the bandwidth is somehow distributed between the target and the controllers and the interferers, but I don't want to go into excessive depth on this. So I hope these plots are clear. If they are not, just tell me now. Okay. The other two workloads of interest are these ones. In this case, the failure is about the total throughput. As you can see, the sum of the heights of the bars in case of I/O cost is much lower than the case with BFQ. It's extremely lower. So there is a high loss of throughput, both in this case where there are sequential readers against a sequential reader as a target, and in the case where there are sequential writers as interferers and the sequential reader as target. So this is the second type of failure. So first type, failure in guaranteeing bandwidth to the interferers in this case, but there are other examples where the failure is for the target, and in this case, failure to reach a high throughput. Okay, so this is the problem. So I started analyzing it. To do that, I made a patch to trace what happens inside I/O cost. And this is what I found. The root cause for all this failure is this one. Drives have a very complex transfer function because they have multiple channels. They have pipelines inside the channels, they do striping, there is parallelism that depends on locality, there is interference among workloads inside the drive, there is read ahead, request reordering, garbage collection, wearing, and a lot of complex stuff. So for this reason, the parameters of the transfer function of these drives are non-linear. They vary with time, they vary with workloads, and they are hard to know or to size. So the transfer function is a function that tells us the output, so what happens, which I/O requests are served and when, as a function of the input, the I/O requests that we dispatch to the drive. So complex transfer functions, and the problem is that I/O cost and I/O latency control I/O exactly through these parameters. In particular, I/O costs are the parameters used by the I/O cost controller. So the I/O cost controller uses the I/O costs, the cost of each I/O as a parameter to control I/O, and uses device saturation. So how loaded the device is. And these are exactly the parameters that are not linear, that vary with time, that are hard to know precisely. So depending on the actual transfer function, it may be hard for the controller to actually control the bandwidth of the groups and to boost the throughput. So I know that these details are maybe somehow not so apparent. The problem beneath all these details may be not so apparent. So I will go for a real life example that maybe will help us grasp the essence of the problem. Then I will apply this real life example to the failure of I/O cost. So here is my real life example. Building where it has been put a little or absolutely no care in having a stable and easy to control system for heating water. An example is, unfortunately, my house. So suppose that you want to take a shower in such a building. Getting the shower temperature right may be a problem in this building, because when you rotate the knob of the shower, you stimulate in a nonlinear way a nonlinear system. It is a system that reacts with time varying delays. So here is what happens. If you don't know these parameters well enough, you may fail to control the temperature successfully, because you may get too hot water or too cold water until maybe you learn how to rotate the knob. But even after you learned that, so you made it, so you have control on your temperature, there may still be external events may change these parameters, so you get burned again, even if you didn't touch anything. So I hope that this example gives you good insights on the actual problem. So for I/O costs, controlling I/O, so guaranteeing fairness and reaching a high throughput is as difficult as getting the shower temperature right in my example building. That's the idea. Now I will focus and I will show you some details only for one failure, the throughput failure. If you want, I have extra slides about the other failure. Let me tell you very, very succinctly the parameters used by the I/O cost, because I will show parameters. So I/O cost has the throughput through a parameter named V rate, which is computed as a function of the busy level of the drive, that is how busy the drive is, and as a function of how many groups are lagging behind their target service, and finally as a function of the device saturation computed through latency of I/O, but I don't want to go, again, not to give you too many details. But this busy level and number of groups lagging are a function of the estimated service received by each group. So they are a function of the I/O costs, but I/O costs are subject to high imprecision for all the reasons that I've already told you, and they are time variable. So this is what happens. This is a trace of what happens in the failure where there are only reads. So the throughput failure with only reads that I showed you. You can see the red line is the V rate, so how the controller sets the speed of the drive. And as you can see, at the beginning, everything is okay, but then there is this drop here, and the drop happens because, as you can see, there is this peak in the busy level. For some reason, the controller believes that the drive has become suddenly extremely busy, which is completely false. So it drops the V rate, so it just slows down the drive for no reason reason, and then it keeps it very low. Then there is some other fluctuation where it seems to realize that actually the busy level is lower, but then when it tries to increase V rate, again a peak, so the V rate goes down. Then again here a very high peak, even lower V rate. Then it tries to increase again the V rates, but there is a high number that you can see with the green here, a high number of groups lagging behind the target service. And in this case, it's harder because of the algorithm to increase V rate quickly. So the ultimate result is that on average, the throughput is extremely low for no reason. The drive is completely underutilized. So that's the reason for the failure. Similar failure with the writes, but I don't want to steal time to Anders. So believe me, this is the same problem with different cures. So to wrap up, IO cost and IO latency for sure have been crafted very skillfully and have been tuned to get the shorter temperature right on the machines of the others of these controllers. But if the transfer function varies, then these it may be hard or even impossible for this controller to win, to control IO. Why does BFQ make it? I will leave this on extra slides. I don't want to comment on this. If you want, I will tell you now. I don't want to steal time to Anders. So for me, this is all. This is all for my part, and I hand it to Anders. So let me switch back to not full screen and stop sharing.
That's okay, Paolo. Anders can just start sharing straight away.
Okay. Thank you, Phil.
About
Okay.
how we try to test Paolo's stuff, and I'm working for a project called LKFT, and today we only do functional testing, and Paolo's been my guinea pig for benchmark tests. And as Paolo pointed out, he found some issues, and to present and to find all the regressions, we've done endless loops how to do this. First, we think we need, or I'm going to make this really short instead. Can we run on any platform and do the test, or do we need to have one hardware and one peripheral and run that over and over again? Or can we have a pool of devices and peripherals to run? That depends on benchmarks, what we want to benchmark. And for Paolo's S-Suite, we think we can use a pool of targets, because it's only a regression if it's more than 10%. That's what we're going to start with, at least. And we will use a tool called Squad Client to do email reporting at the end as well. But I think I'm going to stop here. We're out of time.